The next presenter has recently joined GSWA. She's a senior geologist and comes to us with over 20 years of oil and gas experience, most recently as a geologist in exploration and development at Woodside. She's going to tell you a little bit more about the data and interpretation products of the Atlas. Welcome, Courtney Brennan.
Thank you for coming today. I'd like to start by thanking Carrie-Anne Winmar for her gracious welcome to country and state what a privilege it is to be studying the geology of such a culturally significant landscape. So I'm here today to continue the story of a carbon dioxide storage atlas. Tell you a little bit about the story of how we put together our data products that are available for you online. So thank you, Deirdre, who just now spoke of that urgent need for carbon dioxide sequestration and the state government's support by providing an atlas of carbon sequestration relevant data available for easy download. But who is this data for? Where did we get it? And what did we do with it before we made it available for you? So the biggest and simplest answer is it's available for everybody. Whether you're interested in analysing for sequestration potential, geothermal energy, whether you're in conventional exploration, perhaps looking for sedimentary hosted minerals. We're covering all the major basins of Western Australia and providing relevant data products that anyone can use, but that are particularly pertinent for carbon dioxide sequestration. So today, I'm going to illustrate how we go about putting these products together by focusing on the temperature data. And the reason being that's that critical need to meet the pressure and temperature conditions to effectively store carbon dioxide in a dense supercritical state, but also because we have two end members of data available, raw measurements and interpreted products such as maps. So let's get into it. So we need quality information when we're making any type of important decision, and sequestering carbon dioxide is no different to that. We need to understand the underground pressures and temperatures so that we can store that carbon dioxide in its supercritical state. The temperature data that's available in the Atlas is a time-saving collection made from open file reports that have been obtained by operators over many decades. These measurements are made during a variety of tests, whether production tests, drill stem or DST tests, or bottom hole temperature, which I'll often call BHT, bottom hole temperature measurements made during the drilling process. Why do we need more than just the temperature and the depth? Even for something as simple as a measured temperature, we need to understand the context of how that measurement was made to really correctly use that data in a meaningful way. You'll see on the right-hand side of this slide different criteria that we're recording in that spreadsheet that you can download for any basin right now on our atlas, including both the depth, the temperature, the type of test, because this will affect how accurate the measurement was, the circulation time, and I'll explain that briefly in a second, and also the time since circulation. So what kind of context would we be looking at here? If we consider the simplest type of test, the bottom hole temperature measurements, when we're drilling a well through some stratigraphy, and I've got some cartoon stratigraphy there in the different coloured layers, let's imagine that that grey polygon there is a long, thin drill well filled with mud, and that mud serves the purpose to safely and effectively keep the fluids in those layers of rock underground. Now, the measuring device is on the drill string, which is sitting at the bottom of the well, but it's in the fluid. It's not touching the rock that we want the rock measurement from. It's measuring the temperature of the mud. This is important because the mud comes from the surface, where it's injected underground and circulated around. And as you get deeper and deeper underground, we know that those rocks are going to get hotter. It means that we're going to have to give that mud time to warm up, which is why the types of measurements about circulation time, how long we're circling the mud through the well, and the amount of time since we stop circulating to let the mud warm up are really important when we want to correct those measurements to represent the temperature of the rock itself. So you can see mud's a little cooler, let it warm up, it's starting to represent the rock temperature. So we can talk about uncorrected measurements or corrected measurements, and that's the type of process we're referring to there. So as an example, let's look at the Officer Basin from the Western Australian portion. We have two graphs here. The one on the left is uncorrected bottom hole temperature measurements, and on the right, corrected measurements. You'll notice there's more uncorrected measurements than corrected because you take a series of measurements to produce the one temperature measurement that's corrected at a depth. On both graphs, the depth is increasing downwards and the temperature is increasing from left to right. So this illustration allows me to tell you three general things about temperature in the subsurface. One, which you can see from both graphs, is that temperature does increase with depth. The second is that the corrected temperatures are going to be higher than the uncorrected temperatures because we're talking about the temperature of the rock rather than the mud that was measured. And the third is that some wells, each coloured dot represents a different well, Some wells at similar depths are warmer than others. So if we take that thought to the next slide, that you're going to have different temperatures at the same depth in different areas, we need to start to consider, how do we understand the way temperature changes across an area as well as within a well? So here's the Officer Basin again. It's a good example for a few different reasons, and one of them is it's relatively unexplored. There's heaps of potential there, and it's a really interesting basin. And one of the interesting things about it is it's really old, and, which for me, working in hydrocarbons and dinosaur age rocks, looking at stuff that predates macrofossils is incredible. But you can see where we've put the stars. This is the well coverage that we've got in our model. But it's a really large area, even just the Western Australian area. How do we understand about the way temperature is going to be changing underground for the rest of that area? So we need to be able to find some way to model it. Let's look at, this line here is representing the top of the Brown Formation. So the Brown Formation is a really old, it's a Neoproterozoic formation that's salt dominated. So it does some cool things. You can see some salt diapirs in there, and Rob's going to show you that a little bit later in his presentation as well. But let's go models. So when I say using a model, I'm not saying that the model is the measuring tool or that the model is some all-seeing, all-knowing entity. A similar theme to what was mentioned earlier with AI. You get in something comparable, you get out what you get in, and you need to think about the context of what that means. So the same way that this cartoon model has a few characteristics that are sufficient to describe a human, the models that we create, whether they're contextual, which might just be a verbal description, or computerized, a computational model, which is a digital representation of the elements, we need to capture each of those things that we think will impact what we're trying to understand and find mathematical equations that actually govern those interactions between them as well. Essentially, we're using our model as a calculator, a very fancy calculator, but we're the ones that need to have a good think about what we're putting in and what we're asking of our calculator. I'm going to spend a couple of slides going through how we've done our temperature modelling using a type of software called GSWA, which for anyone in oil and gas in the audience might be familiar with it for its basin modelling and charge evaluation type prospects. Continuing with the Officer Basin, I need to take what we know about our wells and represent that for each well in some way that then we can add that into our calculator. There's a subset of GSWA called Genesis, and this looks at the well by well representation. We need to input depth-dependent data to describe what's going on in the well for not only temperature, but also the rock formations that are there, because these are things that we can carry across to other wells. This is what we're going to use to carry our understanding of things that relate to temperature in the areas where we have no wells. And we can use seismic maps to do that, and I'll touch on that in a minute. But we need to look at formation tops within the well, the composition of the formations within the well as percentages of standardised rock types so that it can make calculations about how they should behave through time, and describe also the lithology and the age, because that will help us actually understand how things were buried through time. So this example of Ualga 3 is from the Officer Basin. You can see on the top left there's a representation of the well with its lithologies. Within each formation there's a percentage of each rock type, but it's standard across the whole of the formation interval. There's times that represent what ages these were deposited. There's the temperature measurements. And from these we can use Genesis to help us draw a line. Say the top right-hand side is a graph of the temperature depth relationship that we can draw through the temperature measurements, and we can make those specific for each well. And the plot on the bottom describes the way that the modelled well would have formed as it got buried through time. So these sedimentary rocks are forming at the surface, they're being buried by subsequent sedimentary rocks on top of them, and they get deeper through time. So I'm going to show you a couple of slides just to explain what I'm illustrating with these burial diagrams, because if you haven't seen them before, it just looks a bit weird, but when you walk it through, you can see how that would actually characterise in a numerical way what's happening in one location, and imagine that we can spread that across a map. All right, so let's do it. We have, on that bottom right graph, a time axis along the top. Long ago is on the left, coming all the way through time to present day on the right. At that red circle represents present day for time and also present surface for depth. So that's 0, and then you get deeper as you go down. So, to illustrate how you would put together one of these, let's imagine the Brown Formation forming a really, really long time ago. As you can see, I've put a little star so that we can track that location of that bottom depth as it goes through time. Where the line intersects the time horizon is when you can imagine that that rock was forming at the surface, and then the bulk above it is the rock that's come later. As we go through, you can see sometimes it's getting buried more quickly than others with more rock over that interval of time, and it gets deeper and deeper the more layers you put on top. We're able to account for erosive events by adding in values for the duration and the amount, duration of time that the erosive event took place and the amount of sediment that was removed. So we can do that, model a succession of those if required. Here for the Officer Basin, you can see now this picture is representing around the time of the Table Hills volcanic event, and you'll notice that previously things got buried rather quickly, but from this point onwards, deposition at this area was much slower, as you can see by a flatter line through time describing that lower burial rate. And this brings us to the present day representation that we're modelling with the well. Once we've done this for every well that we want to consider in our model, we're ready to find a way to connect them in a meaningful way and use properties that we think should be influencing temperature, but properties that we also can describe based on the data that's available. Basically, that means we're going from 1D to multi-1D. And the reason we're doing multi-1D rather than 3D is that we're talking really, really large areas, whole sedimentary basins, or the Western Australian half for the Officer. And also the data density is not the same as for a field development where you might have seismic mapping individual sand layers, for example. We're talking large areas here. So multi-1D and Trinity and GSWA was the appropriate choice there. So there's a few steps involved. We need to find a way to relate what we know about each well and what we know about how that relates to the connections between the wells. So to do that, we're going to define a type section, if you will, a standard temperature depth curve. This curve doesn't need to match any one specific well, but we're going to use Trinity to find a way to relate it to every specific well. So think of it as a key that we're using. So we're using all our temperature data to draw a general line that becomes our standard line, and that is our temperature depth curve that we're operating with. So then, another input is a scalar map. So we generate some of our inputs in the modelling process, and one of those is the scalar map. This is the other part of that key that helps us describe what the temperature depth relationships are anywhere on the map area. So for example, this map represents the area where the top of the Brown Formation has been mapped seismically, but the values on the map represent how the temperature depth curve relates to the standard curve. Numbers smaller than 1 have a smaller temperature depth gradient, and numbers bigger than 1 have a larger gradient than the standard curve. What that means is, in the red areas with the small numbers, you have to drill deeper to get to the same temperature as you would in a high value area, which is coloured yellow or green. We know a standard curve, we can relate the temperatures in each well to our standard curve in a mapping sense. Let's now take the structure of those rock formations to connect and add that last input that's required. So let's add our seismically interpreted depth maps. So again, this is describing the top of the Brown Formation, but the coloured parameter that's illustrated is depth. Depth below, in this case, the seismic datum. The colour scale is showing red is shallow and blue and green is deep. Put all those together in our calculator, we can generate our temperature maps. So same surface, but now we're talking about the temperature. Blue is cool, red is hot. Awesome thing about the Brown Formation, we're calculating that in a regional sense, everywhere meets that temperature requirement. So now we can take that final step, we can illustrate how we can screen for supercritical carbon dioxide storage. Deirdre was illustrating that process of going from large-scale considerations and triaging as you go along. We're talking about the basin screening, the first stage of that process here. So we know we need the 31.1 degrees, 1070 psi. We also need some rock to hold it. The deeper it gets buried, the more the porosity might get occluded. So let's, at a broad sense, consider above 3,000 metres as a first pass. You can see everywhere on this map meets that 31.1 requirement. The same process is used to calculate pressure, and the red dashed line is the isobar for the 1070 psi for this surface calculated with models. So you can see most of that map already meets supercritical conditions. You add that need for quality reservoir potential, and we still have a really large area of this formation available. Not everywhere will have reservoir, but that is the point of the site selection process that would be next. I'll finish up now. Coming soon, I'm really excited to get out to you all some formation top information that we've been putting together for the Northern Carnarvon Basin. So over 200 wells, both in state waters and onshore, and I'm really looking forward to you seeing them soon. In summary, lots of data, some there, some coming soon, and thank you so much for your attention.